There is a moon orbiting Jupiter right now that NASA has known about for decades. Scientists have photographed it, studied it from afar, debated about it in conference rooms, written papers about it, and argued over what it might be hiding. And yet, in all of that time, not a single dedicated spacecraft has ever been sent there specifically to investigate it up close. No lander, no orbiter pointed at it alone, no probe designed with it in mind, just distant observations and a whole lot of unanswered questions. And what makes this even stranger is that the things scientists suspect might be happening on this moon are some of the most extraordinary possibilities in all of planetary science. We are not talking about something boring. We are talking about a world that might be more geologically active than anything else in the entire solar system. A moon that could be reshaping itself constantly. A moon that might hold clues about how life begins. A moon that sits inside one of the most brutal radiation environments humans have ever documented, bombarded by particles so energetic that any spacecraft we send near it risks being cooked from the inside out. This is not a forgotten world. It is a deliberately avoided one, and the reasons why NASA has stayed away tell a story that is just as fascinating as the moon itself. So stick around, because by the end of this, you are going to understand why this particular moon keeps scientists up at night, why exploring it is one of the hardest engineering challenges our species has ever faced, and why the answers it holds could fundamentally change the way we think about where life exists in the universe. And if you find this kind of thing as mind-bending as we do, hit that subscribe button right now, because this is the kind of content we are here to make. Let us start at the beginning. Jupiter has a lot of moons. That is not a surprise to most people. What might surprise you is just how many it actually has. For a long time, the number sat at 67 confirmed moons. Then in 2023, astronomers announced a new count. The total number of confirmed moons around Jupiter jumped to 95. 95. That is nearly 100 worlds orbiting a single planet. And most of them are tiny, irregular, captured objects. Little chunks of rock that got too close to Jupiter's enormous gravity well a long time ago and never escaped. But among all of those moons, there is a group of 4 that stand completely apart from the rest. These are the Galilean moons, named after the astronomer Galileo Galilei, who first observed them through a telescope back in 1610. His discovery of these 4 moons was so important that it became one of the central pieces of evidence that the Earth was not the center of the universe. Here were objects clearly orbiting something other than Earth. Here was proof that not everything in the cosmos revolved around us. Those 4 moons are Io, Europa, Ganymede, and Callisto, and each one of them is a world unto itself. Each one of them is genuinely strange and worthy of study. But one of them is in a category all its own when it comes to sheer weirdness, sheer hostility, and sheer scientific importance. That moon is Io. And the story of how we came to understand Io is one of the most remarkable in the entire history of space exploration. Because for a long time, nobody expected Io to be anything special at all. When the Voyager 1 spacecraft was hurtling toward Jupiter in 1979, scientists had already spent time thinking about what the Galilean moons might look like. They had observations from telescopes. They had some ideas about the composition of these worlds, based on how they reflected light. And their general expectation for Io was that it would look something like our own moon, a cratered, battered, geologically dead rock, something that had been hammered by asteroid and comet impacts for billions of years and just sat there, frozen in time, wearing every scar on its surface. That was the assumption. That was the consensus. And then Voyager 1 arrived. What the spacecraft's cameras revealed when they turned toward Io was so unexpected that the scientists looking at the images genuinely could not process what they were seeing at first. The surface was not cratered, not even a little. In fact, there were essentially no impact craters on Io at all. Instead, the surface was covered in mountains, in plains, in enormous calderas, and in colors. Wild, impossible colors. Yellows and oranges and reds and whites and blacks spread across the surface like some kind of alien abstract painting. And then, just to make things even more dramatic, a mission imaging scientist named Linda Morabito was doing routine navigation work with the Voyager images when she noticed something extraordinary. There was a crescent-shaped plume rising above the edge of Io's visible surface, an umbrella of material blossoming outward into space. At first, she thought it might be another moon behind Io, but the geometry was wrong. This plume was coming from Io itself. It was a volcanic eruption, a massive one, the first active extraterrestrial volcano ever discovered by human beings. And it was not alone. As scientists went back through the images, they found more. 8 separate volcanic eruptions captured in the Voyager 1 images of Io. 8 volcanoes erupting simultaneously on a moon most people had expected to be dead. The scientific community was stunned. And in the days that followed, a remarkable coincidence emerged. Just before the Voyager 1 flyby, a paper had been published by 4 researchers, Stanton Peele, Patrick Casson, and Ray Reynolds, that had predicted volcanic activity on Io based on a theoretical mechanism. They had calculated that the gravitational pulls from Jupiter and the other large moons would squeeze and flex Io's interior constantly, generating enormous amounts of heat through a process called tidal heating. Their paper was published on March 2, 1979. Voyager 1 made its Io flyby on March 5, 1979. 3 days later, their prediction was confirmed beyond anyone's expectations. Tidal heating. That is the mechanism that makes Io what it is. And to understand it, you need to understand what Io has to deal with every single day of its existence. Io orbits incredibly close to Jupiter. It completes one full orbit in just 42 hours. And Jupiter is not small. Jupiter is the most massive planet in the solar system, 11 times wider than Earth, more than 300 times more massive. The gravitational force Jupiter exerts on Io is enormous. It literally pulls the surface of Io toward it, creating a tidal bulge, a physical deformation of the moon's surface that rises and falls as Io moves through its orbit. But it is not just Jupiter pulling on Io. The other large Galilean moons, particularly Europa and Ganymede, are also pulling on Io gravitationally as they orbit. And their orbits are in a specific mathematical relationship to Io's orbit, called a resonance. For every 4 times Io goes around Jupiter, Europa goes around exactly twice, and Ganymede goes around exactly once. This is not a coincidence. This orbital resonance is self-sustaining, and it ensures that Io is constantly being pulled and stretched by gravitational forces from multiple directions simultaneously. The result is that Io's interior is being kneaded like dough, continuously and relentlessly, and that mechanical energy gets converted into heat. So much heat that the moon cannot hold it all inside. It has to release it, and the way it releases it is through volcanism. Constant, unending, extraordinary volcanism, on a scale that makes Earth's most violent geological events look modest by comparison. The numbers surrounding Io's volcanism are almost too large to be meaningful. The total heat output from Io's interior is estimated at somewhere between 60 and 100 trillion watts continuously. To put that in perspective, all of the electricity generated by all of the power plants on Earth combined amounts to roughly 3 trillion watts. Io releases somewhere around 20 to 30 times that amount of energy through its geology every single second of every single day. There are over 400 active volcanoes on Io. 400. On Earth, we count active volcanoes in the dozens, and we consider a major eruption a significant geological event. Io has hundreds of them going at once, all the time. Some of those volcanoes are enormous calderas, depressions in the surface left by collapsed magma chambers, stretching hundreds of kilometers across. The largest, called Loki Patera, is a lava lake roughly 200 kilometers in diameter. Imagine a lake of molten rock the size of a mid-sized country. And the volcanic plumes on Io are staggering. Some of them reach heights of 500 kilometers above the surface. Let that sink in. 500 kilometers. The International Space Station orbits Earth at about 400 kilometers altitude. Io is throwing material from volcanic eruptions higher than the orbit of a space station. The material ejected from these eruptions escapes Io's gravity, spreads through the Jovian system, and forms a torus, a donut-shaped cloud of sulfur and sulfur dioxide gas that wraps around Jupiter along Io's orbital path. Io is literally painting the surrounding space with its own material. The surface of Io is being resurfaced constantly. There are essentially no impact craters, not because Io has been lucky enough to avoid being hit, but because any craters that form get buried almost immediately under new volcanic deposits. The surface of Io is so geologically active that it renews itself on timescales of years to decades. You could photograph Io today and photograph it again in a few years, and the surface could look meaningfully different. It is the most geologically dynamic body in the solar system. Nothing else comes close. So why has it never been officially explored? Why has no dedicated mission been sent to investigate this extraordinary world up close? The answer is radiation. Jupiter has a magnetic field. That is not surprising. Many planets do. But Jupiter's magnetic field is not comparable to Earth's in any reasonable way. It is roughly 20,000 times stronger than Earth's magnetic field. It is the strongest planetary magnetic field in the entire solar system. And this enormous magnetic field does something that creates one of the most dangerous environments in the known universe. A magnetic field traps charged particles. Electrons, protons, ions streaming away from the sun in the solar wind, and particles kicked loose from Jupiter's own moons get captured by Jupiter's magnetic field and accelerated to extremely high speeds. They become trapped in belts of radiation surrounding the planet, similar to Earth's Van Allen belts but vastly more intense. Jupiter's radiation belts are so powerful that they register as the strongest source of radio emissions in the solar system outside of the sun itself. And Io sits right in the heart of these radiation belts. It orbits closer to Jupiter than any of the other Galilean moons. It is bathed in the most intense radiation in the entire Jovian system. The radiation environment near Io is so harsh that the dose a human being would receive there, without any shielding, would be lethal within a matter of hours. Not days, hours. The radiation levels near Io run into the hundreds of thousands of rads per day. A lethal dose for a human being is somewhere around 500 rads total. And radiation does not just kill people, it destroys electronics, it scrambles computer memory, it degrades solar panels, it corrupts data, it can physically damage the structural integrity of materials over time. Any spacecraft we send near Io has to be designed to survive in an environment that will be actively trying to destroy it from the moment it arrives. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, made several flybys of Io during its mission. And those flybys were genuinely extraordinary from a scientific standpoint. They revealed the most detailed images of the surface we had ever seen. They detected the composition of volcanic gases. They measured the magnetic field interactions between Io and Jupiter. They were a treasure trove of new information. But Galileo was not designed for Io. It was designed for the entire Jovian system, and every time it flew close to Io, it absorbed a punishing dose of radiation. Galileo was not built with enough radiation shielding to survive for very long in Io's environment. The decision to use it for Io flybys was made with the understanding that each pass was costing the spacecraft some of its remaining functional lifetime. The mission managers were essentially spending Galileo's life savings every time they sent it past Io. After Galileo, the next major visitor to the Jovian system was the Juno spacecraft, which arrived in 2016. Juno was designed primarily to study Jupiter itself, its atmosphere, its interior, its magnetic field, and its gravity. It was not designed for moon science. But as the mission progressed and the spacecraft outlived its original planned lifespan, scientists began extending the mission and having Juno make flybys of the Galilean moons, including Io. Juno has performed multiple Io flybys, including several relatively close approaches that have returned stunning new imagery. In late 2023 and early 2024, Juno made two of its closest passes by Io ever, coming within about 1,500 kilometers of the surface. The images returned from those flybys were the closest views of Io we had seen since the Galileo era, and they revealed volcanic activity in extraordinary detail. But again, Juno is not an Io mission. It is an extended Jupiter mission that is doing the best it can with a spacecraft not specifically optimized for this purpose. So when we say that Io has never been officially explored with a dedicated mission, that is exactly what we mean. Every piece of data we have about this remarkable world has come from spacecraft that were there for other reasons and happened to swing by. No mission has ever been designed from the ground up specifically to orbit Io, study Io, and answer the central questions that Io raises. Not one. And those questions are significant. Start with the question of what Io is actually made of. We know the surface is dominated by sulfur and sulfur dioxide. The volcanic eruptions deposit these compounds across the surface in layers, creating that wild color palette that stunned scientists in 1979. Different temperatures and chemical states of sulfur produce different colors. Freshly deposited sulfur from an eruption is typically red or orange. As it cools and transforms chemically, it can turn yellow or white. Older deposits often appear dark. This is what creates the patchwork appearance of Io's surface. But beneath the sulfur coating, what are the rocks actually made of? The lava erupting from Io's volcanoes appears to be silicate in nature, similar in composition to basaltic lava on Earth. Temperature measurements from Galileo and Earth-based telescopes have detected volcanic hotspots on Io, reaching temperatures as high as 1,600 degrees Celsius. Some estimates push even higher, up toward 1,800 or even 2,000 degrees Celsius. That is extraordinarily hot for molten rock. On Earth, basaltic lava typically erupts at temperatures between 1,100 and 1,250 degrees Celsius. The fact that Io's lavas appear to be erupting at higher temperatures than typical basalt on Earth raises some very interesting possibilities. Some scientists think it could mean Io's mantle contains rocks that melt at higher temperatures, potentially ultramafic compositions, rocks with a very high magnesium content. Others think it could be related to the way tidal heating is distributed inside Io's interior. A dedicated mission with proper instrumentation could answer this question definitively. Right now, we are essentially guessing from a distance. Then there is the question of Io's interior structure. Does Io have a global magma ocean beneath its crust, a layer of completely molten rock circling the entire moon? Or is the heat concentrated in specific regions that feed into discrete volcanic systems? This matters enormously for understanding how tidal heating works, not just on Io, but on any tidally heated world anywhere in the universe. Data from the Galileo mission provided some hints. The way Io interacted with Jupiter's magnetic field suggested there might indeed be a global layer of conducting material, possibly molten rock, beneath the surface. But the data was not conclusive. It could be interpreted in different ways. To actually resolve this question, you need a spacecraft in orbit around Io, measuring the magnetic field variations continuously over many months, mapping how the interior responds as Io moves through different phases of tidal stress throughout each orbit. That requires a dedicated orbiter, which we do not have. And then there is the most profound question of all, the one that connects Io to the biggest mystery in all of astrobiology. Could Io's volcanism, or the chemistry it generates, be related in any meaningful way to the origin of life? Now, before anyone objects that Io seems like one of the most hostile places imaginable for life, let us be clear. Nobody is seriously suggesting that Io itself hosts life. The surface temperature swings are extreme. The radiation bombardment is lethal to anything biology has ever produced. The sulfur-rich environment is intensely chemically reactive. Life as we know it does not have a clear pathway on Io's surface. But what about the chemistry? On early Earth, volcanic environments were central to many theories about how life began. Hydrothermal vents, where volcanic heat and chemistry interact with water and organic molecules, are considered one of the most plausible cradles for the origin of life. The volcanism creates chemical gradients. It drives reactions. It produces complex molecules from simpler ones. It creates the kind of disequilibrium chemistry that seems to be necessary for living systems to emerge. Io is performing chemistry on a planetary scale continuously. The volcanic gases it releases contain sulfur, sulfur dioxide, sodium, potassium, chlorine, and other compounds. These materials get ejected into space, interact with Jupiter's radiation environment, and spread throughout the Jovian system. Some of them get swept up by other moons. Some of that iogenic material falls onto the surface of Europa, the moon just outside Io's orbit. And Europa is the world where the possibility of life in the outer solar system is considered most seriously. Europa almost certainly has a liquid water ocean beneath its icy crust, kept liquid by tidal heating that, while less intense than what Io experiences, is still powerful enough to prevent freezing. And material from Io's volcanic system may be continuously adding chemical complexity to the surface of Europa, and potentially, through various geological processes, to its subsurface ocean. So Io is not just a volcanic spectacle. It is potentially a chemical factory that has been running for billions of years and distributing its products across the neighborhood. To understand the chemistry of the Jovian system, to understand the conditions that might make Europa's ocean a plausible environment for life, you have to understand Io. And to understand Io, you need to go there. The frustrating reality is that space agencies understand all of this. The scientific community has been making the case for an Io mission for a long time. It keeps appearing on prioritization lists. It keeps being discussed. And it keeps running into the same fundamental obstacles. Cost is one of them. A mission designed to operate in Io's radiation environment is not cheap. Radiation hardening of electronics is expensive. Building redundant systems to handle the damage radiation will inevitably cause over time adds cost and complexity. Designing a power system that can function in that environment while also being reliable enough for a years-long mission is a genuine engineering challenge. These missions cost hundreds of millions of dollars at minimum, and a full orbital mission to Io could easily push into the billion-dollar range. The other obstacle is priority. Jupiter has 4 major moons, and they are all scientifically valuable. Europa's potential ocean has generated enormous interest in the question of life in the outer solar system, which means Europa has captured the lion's share of funding attention. The Europa Clipper mission, launched in October 2024, is on its way to the Jovian system specifically to investigate Europa. It will make dozens of flybys of Europa and gather an extraordinary amount of data about the ice shell, the ocean beneath, and the moon's habitability potential. Europa Clipper is a stunning mission, and its science will be revolutionary. But choosing Europa meant not choosing Io for this particular major mission slot, and major mission slots do not come along constantly. The process of prioritizing missions across the entire field of planetary science, a process managed through the Planetary Science Decadal Survey, which produces a list of recommended missions roughly every 10 years, means that getting a mission approved and funded can take 15 to 20 years from initial concept to launch. Io has been discussed. Io has been advocated for. But Io has not yet risen to the top of that list in a way that resulted in a dedicated mission. There have been serious proposals. Several mission concepts for Io have been developed by scientists and engineers over the years. One of the most developed was called the Io Volcano Observer, or IVO. This was a proposed mission that would have placed a spacecraft in an orbit that repeatedly flew by Io, similar to how Europa Clipper flybys Europa. It was designed to study the volcanic activity, measure the heat flow, investigate the interior structure, and characterize the surface composition in detail. IVO was proposed for the New Frontiers program, a category of moderately priced planetary science missions with a cost cap in the range of $1 billion. It was a finalist for a mission selection in 2021, which meant it made it through multiple rounds of competitive review and was seriously considered by NASA. It was not selected in that round. Another mission in a different category was chosen instead. But the fact that IVO made it that far tells you something important. The scientific community considers an Io mission genuinely important. It is not being ignored. It is being weighed against other priorities and losing by a narrow margin. Meanwhile, the European Space Agency has its own Jupiter mission in flight. The Jupiter Icy Moons Explorer, called JUICE, launched in April 2023 and is on its way to the Jovian system. JUICE is primarily focused on Ganymede, the largest moon in the solar system, which also has a subsurface ocean and its own magnetic field. But JUICE will also perform flybys of Europa and Callisto during its approach phase and will eventually settle into orbit around Ganymede. JUICE is not an Io mission either, though it will gather some data about Io from a distance. So right now, in the 2020s, we have 2 major missions heading toward Jupiter. Both of them are focused on the question of potentially habitable ocean worlds. and neither of them is primarily focused on the most geologically extraordinary world in the solar system. Let us talk for a moment about what we have actually learned in the decades since Voyager, because it is genuinely impressive, even with all of the limitations we have discussed. The Galileo mission's Io flybys, conducted from 1999 to 2002, when the mission was extended specifically to allow closer Io approaches after Galileo had already accomplished its primary science goals, returned stunning data. The closest flybys brought Galileo within just a few hundred kilometers of the surface. The imaging from those passes revealed details of volcanic structures that nobody had expected, individual lava flows, collapse features in volcanic calderas, mountain building processes unlike anything on Earth. The mountains on Io, by the way, deserve special mention. Io has mountains. In fact, it has some of the tallest mountains in the solar system. The tallest, Beau Saule Montes, reaches a height of about 18.5 kilometers. Compare that to Mount Everest on Earth at 8.8 kilometers. Io has a mountain more than twice as tall as the tallest mountain on Earth. But the way these mountains form is completely different from how mountains form on Earth. On Earth, mountains are generally built by tectonic processes, the collision of crustal plates pushing material upward. Io does not appear to have plate tectonics in the conventional sense. Instead, the constant deposition of new volcanic material across Io's surface means that the surface is constantly being buried, layer after layer after layer, and the compression from all of that burial causes the underlying crust to buckle and thrust upward, producing mountains in a process called thrust faulting. The volcanism creates the mountains indirectly by burying the crust so fast and so heavily that it breaks and pushes sections of itself upward. These mountains are not volcanoes, they are tectonic structures produced by a volcanic process. Io somehow manages to have both the most intense volcanism and significant tectonics, but they are connected in a way that has no parallel anywhere else we have ever studied. Then there is the interaction between Io and Jupiter's magnetic field, which is one of the most physically remarkable phenomena in the solar system. Io orbits within Jupiter's magnetosphere, and as it moves through the magnetic field lines, it generates an enormous electric current, a flow of charged particles that travels along the magnetic field lines from Io down to the surface of Jupiter itself. This is called the Io flux tube, and it carries roughly 1 trillion watts of power. 1 trillion watts, flowing continuously between a moon and a planet through a magnetic conduit spanning hundreds of thousands of kilometers. This interaction creates bright spots in Jupiter's atmosphere, called auroral footprints, where the current impacts the planet and excites the gases there, causing them to glow. Juno has imaged these auroral footprints in detail. They are a direct visual signature of Io's electromagnetic influence on Jupiter itself. No other moon in the solar system has this kind of documented, visible, ongoing electromagnetic relationship with its host planet. Io is electrically coupled to Jupiter in a way that is unprecedented in our experience. What a properly equipped orbiting spacecraft could tell us about this interaction is extraordinary to consider. We could map the details of the flux tube current in 3 dimensions. We could understand how it changes with Io's volcanic activity. We could learn how the energy gets distributed into Jupiter's magnetosphere and ultimately into its atmosphere. We could use it as a probe of Io's interior, because the way conducting materials in Io's deep interior interact with the magnetic field tells you things about where those conducting materials are and how they are distributed. The magnetic data from Galileo was tantalizing but incomplete. The flybys were too brief and too infrequent to build a complete picture. You need an orbiter. You need continuous measurement over many orbital periods. You need the kind of data that only sustained, dedicated presence in Io's environment can provide. Now, some people who follow space exploration closely might ask about the challenges of actually getting a spacecraft into orbit around Io specifically, as opposed to making flybys. And this is where things get genuinely complicated from an engineering standpoint. To get into orbit around Io, a spacecraft first has to get to Jupiter. Jupiter is far away. It takes years to get there even on an optimized trajectory. Once you are in the Jovian system, you need to slow down enough to be captured by Jupiter's gravity. That requires a significant propulsion burn. Then, To get close to Io and stay there, you need additional propulsion to lower your orbit. And then to actually orbit Io itself, you need to slow down further and be captured by Io's relatively weak gravity. All of that propulsion requires fuel, and fuel means mass, and mass means you need a bigger rocket to launch all of it, which costs more money. The propulsion challenge alone is significant. But the real nightmare is the radiation. Even during the time it takes to maneuver into an Io orbit after arriving at Jupiter, the spacecraft would be passing through the radiation belts repeatedly. Every pass through the belts adds to the cumulative radiation dose on the spacecraft's electronics. By the time you actually achieve Io orbit, your spacecraft may have already absorbed a substantial fraction of its total radiation tolerance, leaving less budget for the science operations phase. This is why flyby missions are more attractive from an engineering standpoint. In a flyby mission, you spend most of your time in a wide orbit around Jupiter that keeps you away from the worst of the radiation environment. You only dip close to Io for a few hours at a time before retreating back out to safer distances. You sacrifice the continuity of data that an orbiter would provide, but you extend the life of your spacecraft enormously. But even flybys are not simple from a radiation perspective. The radiation dose near Io during even a brief flyby is intense enough that spacecraft designers have to use radiation-hardened electronics throughout the entire system. Every computer chip, every sensor, every memory component, every power system, every data interface has to be designed to continue functioning after absorbing enormous doses of ionizing radiation. This is not off-the-shelf technology. It is custom, expensive, and in some cases involves components that are not even commercially available because there is not enough demand for them outside of space applications. Juno, despite not being an Io-focused mission, provides a good lesson here. Juno was designed with a radiation vault, a thick titanium box that houses its most sensitive electronics and provides additional shielding beyond the basic structural elements of the spacecraft. Even with this protection, the Jupiter radiation environment has been taxing Juno's systems over its extended mission lifetime. An Io orbiter would need even more robust protection. There is also the question of thermal management. The radiation environment near Io generates heat inside the spacecraft's electronics that has to be managed. The volcanic environment of Io itself means that if a lander were ever attempted, the spacecraft would have to deal with terrain that could be anything from frozen sulfur to fresh lava. The engineering requirements for any kind of surface mission to Io are so extreme that such a concept has barely even been seriously studied. An orbiter is hard enough. A lander is essentially in the category of a future generation challenge, and yet scientists keep thinking about it, because Io keeps being fascinating, because every time a spacecraft swings by, it reveals something new and unexpected, because the questions it raises are fundamental ones about how planetary bodies work. In 2022, Juno's flyby imagery revealed volcanic features that had changed since the last time anyone had looked carefully at that part of Io's surface. New lava flows, altered calderas, regions that had brightened or darkened as volcanic activity deposited new material. Io is not waiting around for us to pay attention to it. It is constantly doing something remarkable, and we catch glimpses of that activity through the windows of passing spacecraft that were designed for something else. The 2023 and 2024 Juno close flybys of Io were genuinely exciting events in the planetary science community. The images returned showed active lava lakes glowing with thermal emission. They showed mountains with shadow detail that allowed scientists to estimate heights and study the geometry of Io's rugged topography. They showed regions near the poles that had never been imaged well before, revealing volcanic structures in areas that had been largely unknown. And even from these brief encounters with a spacecraft not designed for the job, scientists learned new things. The distribution of volcanic activity across Io's surface shows patterns that do not perfectly match what the tidal heating models would predict. The heating models suggest that volcanic activity should be concentrated at specific latitudes and longitudes based on where tidal stresses are greatest. But the actual distribution of observed volcanic hotspots on Io does not precisely match those predictions. Either the models are missing something important about how heat is transported inside Io, or there is something about the interior structure that changes how the tidal energy is deposited. Resolving this discrepancy requires better data, more observations, more complete surface mapping, more thermal measurements, more interior probing, all of which requires a mission designed for the purpose. The interplay between what we know and what we do not know about Io is almost dizzying when you lay it all out. We know it is the most volcanically active body in the solar system. We do not know precisely how heat gets distributed from its interior to its surface. We know it has a silicate mantle and is erupting high-temperature lavas. We do not know whether it has a global magma ocean. We know it has mountains formed by compression. We do not know the full details of how this compression cycle operates or how stable these mountains are. We know Io's material is spreading through the Jovian system and reaching other moons. We do not know the full chemical complexity of what is being delivered and what happens to it. These are not trivial questions. They are not academic puzzles that would be nice to solve someday. They are central to understanding how planetary bodies work in general, how tidal heating operates throughout the universe, and how the Jovian environment shapes the possibility of life on the moons around Jupiter. Because here is the thing that ties all of this together. We are increasingly finding that tidal heating might be one of the most important energy sources for creating habitable conditions on moons around gas giant planets. Europa's ocean exists because of tidal heating. Enceladus, the small moon of Saturn that jets water vapor into space from geysers, has its own internal heat source believed to be tidal in origin. Titan, Saturn's largest moon with its thick atmosphere and liquid hydrocarbon lakes, has geological activity connected to tidal processes. As we discover more and more exoplanets, many of which are gas giants orbiting other stars, the moons around those planets become candidates for habitability based exactly on this principle. Io is the laboratory where we can study tidal heating at its most extreme. It is the place where tidal heating is so powerful and so obvious that we can measure it directly, study its effects in real time, and build the understanding we need to interpret what is happening on other tidally heated worlds throughout the galaxy. Io is not just interesting for its own sake. It is the key to unlocking a broader understanding of how energy from gravitational interactions shapes the habitability of worlds everywhere. This is why the scientists who advocate for Io missions are so passionate about it. They are not just moon enthusiasts. They are researchers who understand that Io represents a unique and irreplaceable scientific opportunity. The extreme environment is not just an obstacle. It is part of what makes Io so valuable. Nowhere else can we study tidal heating this intensely. Nowhere else can we watch a world reshape itself in real time. Nowhere else can we see a moon electromagnetically coupled to a planet in such a visible and measurable way. The next decade could bring significant changes to this situation. The IVO mission concept is likely to be proposed again in future mission selection rounds. The scientific case will be bolstered by whatever Europa, Clipper, and JUICE learn about the Jovian system, which may in turn highlight the importance of understanding Io's contribution to the system as a whole. New technologies, including better radiation-hardened electronics developed for space and defense applications, may reduce some of the engineering challenges that make Io missions so daunting. There are also emerging possibilities in the form of smaller, cheaper spacecraft concepts that accept the radiation damage risk more explicitly. Rather than building a spacecraft designed to last for years in Io's environment, the idea would be to build something that is purpose-designed for a shorter mission of perhaps months, accepting that the radiation will eventually win, but getting maximum science in the time before it does. Something like a radiation sacrifice mission. It is a different philosophy from traditional spacecraft design, but it might provide a pathway to Io observations that the traditional approach cannot. There are even concepts for very small spacecraft, CubeSat-class instruments, that could be delivered to the Jovian system as secondary payloads on future missions, potentially flying much closer to Io than a primary mission would risk, because their loss would not be catastrophic to the overall mission. Small instruments that perform a targeted measurement and then fail, having accomplished their specific purpose. Science done on a shoestring by tiny machines that are not expected to survive. None of this is happening tomorrow. Space exploration moves slowly. The timeline from concept to launch to arrival at Jupiter and then to science operations is measured in decades. The scientists writing papers today about what they want to learn from Io may be well into their careers or even retired by the time a dedicated mission arrives. but the questions will still be waiting. Io will still be there, churning away, erupting continuously, reshaping itself, throwing material into space, interacting with Jupiter's magnetic field, demonstrating in the most dramatic possible terms that a world without any liquid water, without any of the conditions we typically associate with life, without any protection from radiation, can still be one of the most dynamic and energetic environments in the entire solar system. That is what Io tells us about the range of possibilities for planetary worlds. That geology does not require the conditions that seem normal to us on Earth. That energy comes in forms beyond sunlight. That activity and change and dramatic processes can occur in places that look at first glance like they should be frozen and dead. In 1610, Galileo looked through his telescope and saw 4 points of light moving around Jupiter. He watched them night after night, tracking their positions, and he understood that they were orbiting the planet. He did not know what they were. He could not have imagined what they actually are. He just knew that they were moving around something other than the Earth, and that was enough to change the course of human understanding of our place in the cosmos. 400 years later, we know so much more. We know that those 4 points of light are 4 extraordinary worlds, each one unlike the others, each one telling a different part of the story of how the solar system works. And one of those worlds is a volcanic inferno that is actively hostile to any spacecraft we try to send near it, which is exactly why we have never sent one specifically to answer its questions. But we will. Eventually a mission will be approved. Eventually an orbiter will arrive at Io. Eventually the months of continuous data will flow back to Earth, and scientists will begin to understand Io not just from glimpses and flyby snapshots, but as a complete world seen in full detail over time. The interior structure will be mapped, the heat flow will be characterized, the volcanic chemistry will be understood, the magnetic interaction with Jupiter will be fully described. The mountains and calderas and lava lakes will be studied with the kind of instrument suite that only a dedicated mission can provide. And when that day comes, we will probably find that Io is even stranger than we thought, because that is what has happened every single time we have looked at it more closely. Voyager expected a cratered rock and found an erupting volcanic world. Galileo found volcanic temperatures higher than models predicted, and mountains formed by processes unknown on Earth. Juno found volcanic activity in places and of types that challenged the heating models. Every time we look, we are surprised. That is the signature of a world that has more to teach us than we have yet learned to ask about. That is what makes Io not just a remarkable scientific target, but a symbol of why we explore in the first place. Because the universe keeps being stranger and more interesting than our expectations, and the only way to find out how strange is to go there. Io has been known to us for over 4 centuries. We have been sending spacecraft to its neighborhood for nearly 50 years. We have been stunned by what we have found every single time, and yet officially, systematically, dedicatedly, we have never truly explored it. That says something about the limits of what we can currently do. But it also says something about what remains ahead of us. The unexplored is not gone. It is just waiting. Sometimes it is a distant star. Sometimes it is the deep ocean floor. And sometimes it is a moon that has been in plain sight for 400 years, screaming volcanic fire into space, waiting for us to finally decide that it has been waiting long enough.